So far we have been considering the solid as a perfect one, perfect crystalline solid. In other words, there is a regular periodic arrangement of the atoms or molecules in the entire, throughout the entire lattice structure of the crystal. So, we all know that this is an approximation, this is an idealization of the actual situation. In actual practice, defects of different kinds occur, and as we shall see, defects in solids of various kinds are a thermodynamic necessity. It is not just that they occur, but they actually are essential for maintaining equilibrium, thermodynamic equilibrium of the solid. Therefore, the presence of defects is a fact which must be considered, taken into account in order to discuss the properties of real crystalline solids. So, we will spend a little time in this lecture and in the next to consider the presence of defects of various kinds in solids and to some extent their influence on the physical properties. Now, these defects are of different kinds. There can be what are known as point defects. We will consider the point defects today, but there are other defects also, such as line defects. This we already saw this in lecture 1 in the name of topological defects and called them dislocations. So, these are line defects, and then there can be also planar defects in a 3-dimensional solid. So, these we will consider in the next lecture. Today we will focus on point defects. So, point defects by the very name are defects which are of atomic dimensions. We can think of basically 4 types of point defects as follows: a lattice vacancy, which means that an atom or molecule which is supposed to be in a lattice site is missing and a vacancy is created in its place. Then there is what is known as Schottky defect. We will discuss these things in detail, we will just enumerate it now. Then the third one is known as interstitial atoms, which means atoms which are displaced from the regular lattice sites and are squeezed in the interspaces between the atoms, in the interstices. So, they are called, they are also known as Frenkel defects. Then the fourth type is actually an impurity, as we saw in the case of semiconductors, which are deliberately doped with silicon or germanium, which are deliberately doped with pentavalent or trivalent impurities, or even divalent and hexavalent impurities, which are different atoms. So, these atoms go and occupy the position either an interstitial position or a vacant site in the regular crystal's lattice. So, they are impurities which occur in parts per million. So, they also profoundly modify, as we have seen in the case of extrinsic semiconductors, the properties of the semiconductor. So, this can also happen in metals and other solids. So, these are the 4 main types of point defects. We will consider them one by one. First, the lattice vacancy. This can occur because of imperfect packing during crystallization of the solid, or because atoms have been dislodged from their equilibrium positions because of thermal vibrations at high temperatures. Such vacancies can occur in metals or in ionic crystals. At high temperatures. Figure 38(1) shows the presence of such vacancies in an ionic crystal. The vacancies can be in the site of an anion or it can be in a cation vacancy. An ionic crystal has anions as well as cations. The vacancies can be in the place of anion or in the place of the cation. So, both can create vacancies. Now, we mentioned that the presence of vacancies is a thermodynamic necessity. In order to understand this, let us follow the following argument. Suppose the crystal has n atoms. We wish to investigate the situation where, in addition to these n atoms, there are also a small number n of vacancies. So, of the n atoms, these many atoms small n are removed in order to create vacancies. So, there are n vacancies in a total of n atoms. So, there are many ways of choosing or distributing these vacancies. So, the ways of distributing the vacancies. This will be given by the usual formula. So, these are the total number of ways, and because of this there is a configurational disorder and therefore an entropy associated with it, which is given by the famous Boltzmann formula Kb log, suppose we call it W. So, this is S. So, there is a at any finite temperature T, equilibrium temperature, T, we know that thermodynamic equilibrium is established by minimizing the free energy associated with it. So, this free energy will be F equals U minus Ts. We neglect a small term associated with a possible volume change. So, if that is so, delta F is delta U minus T delta S at constant temperature, where U is the internal energy. S is given here and T is the temperature. Now, delta U is due to the creation of these vacancies. Suppose E is the energy associated with the creation of a single vacancy and there are n such vacancies. So, this would be the change in internal energy due to the creation of n vacancies. Each, this is the energy of creation of a vacancy. So, we have to minimize delta F. In other words, in order to do this, let us write delta F explicitly. In order to evaluate this, where factorials of large number of atoms n very large, then we can use Stirling's formula, which is a very good approximation in such situations. So, there, which says log n factorial is n log n minus n, and same for any other term like n minus n and so on. So, using this we can write this as so, using Stirling's formula, so this cancels off, leaving us with so that is the change in free energy, and we want this to be a minimum. For a minimum, the derivative with respect to n, small n of the free energy should be set equal to 0. So, for minimum free energy, for thermodynamic equilibrium, So, differentiating this, we find by simplifying since n is very large compared to n, we can just say this is equal to n by n. So that we can get an expression n equal to n exponential minus EV by kBT. That tells you the number of vacancies in as a function of the total number of atoms and the energy of creating the vacancy and the absolute temperature. Kb is the Boltzmann constant. So, usually the energy involved EV is of the order of 1 electron volt. So, substituting these at a temperature of T equal to 1000 K, which is a sufficiently high temperature, n is 10 to the power minus 5 n. So, a very small number, but a very significant number. It is 1 in 10 to the power 5 atoms. So, the vacancy concentration is quite appreciable, and this is necessary in order to establish thermodynamic equilibrium and minimize the free energy. To produce vacancies in an ionic crystal, for example potassium chloride, what one can do is add a divalent metal like calcium chloride to potassium chloride. So, you grow KCl crystal with controlled amounts of calcium chloride, and the divalent calcium Ca2 plus occupies the regular lattice site, which is goes into the potassium site. So, in order to establish charge neutrality, we have a positive ion vacancy. So, this is shown in the figure here, how substitution of calcium 2 plus ion for a K plus ion gives results in a cation vacancy. In metals, vacancies can be created by the so called process of plastic deformation or rapid cooling from high temperatures, which is a process known as quenching, or bombarding the metal with energetic particles like neutrons, or irradiating the metal with high energy radiation like gamma rays. Next, we consider the next kind of vacancy, namely the Schottky defect. This is the second type of point defects. So, this is a pair vacancy. So, a vacancy pair, not a single vacancy. So, these are found in ionic crystals. So, these are pairs of oppositely charged ions. Obviously, this means that charge neutrality is automatically established. So, it is energetically more favorable to create vacancies in both sides, anion as well as cation side, so as to ensure charge neutrality. So, this is obviously costs less energy. So, that is illustrated in the next figure, where you start from a perfect ionic crystal and then an ionic crystal with point defects of the Schottky type, which means that there are equal number of positive and negative ion vacancies. So, this is energetically favorable, more favorable than the creation of single vacancies, because of the restoration of charge neutrality. So, energetically more favorable than the creation of single vacancies. Which involve charge imbalance. So, if we want to find the concentration of these, the pair vacancies, the concentration is there will be a factor 2, the activation energy is reduced to half. E is the energy required to create the vacant pair. We can arrive at this by a procedure similar to what we did in the case of vacancies. So, the energy of formation of this E pair is 2.02 electron volts in sodium chloride. Incidentally, the introduction of such vacancies opens up the possibility of establishing charge neutrality in a different way other than producing pair vacancies like the Schottky pair. This is done in the so called F center, which is known as a color center. Color center is because these production of these F centers renders an otherwise uncolored specimen into colored. So, it imparts a color because of the characteristic optical absorption. Now, the composition of this is that of an electron trapped in such a vacancy. So, this is an anion vacancy. Suppose we do this by annealing the crystal alkali halide. Crystal in the vapor of the metal. If it is KCl, the vapor of the K, the potassium. So, the excess potassium atom creates a potassium cation and therefore, anion vacancy and an electron. So, K gives K plus anion vacancy for charge neutrality plus electron. So, this is the F center. So, the electron bound to this anion vacancy is known as the F center. F for Farbe, which is the German word for color. So, the production of such a F centers is shown in the next figure. Shows such an F center in an ionic lattice, and its characteristic optical absorption line is a band is also shown, absorption band in KCl is also shown. It occurs around 550 nanometers. So, it behaves like a hydrogen atom, because there is an electron bound to an anion vacancy. So, when the electromagnetic radiation in the form of light is incident on the ionic crystal with such F centers, there is an absorption band with a peak at a wavelength which lies in the visible range. Because of this, the crystal appears colored. To be exact, this is 565 nanometers in KCl. Because of this, the KCl crystal, which is otherwise transparent, appears colored. KCl appears colored, has a magenta color. With the introduction of these F centers. In sodium chloride, the absorption band lies at 4 NaCl, this lies at 460 nanometers. So, the crystal appears yellow. There can be other electronic centers. The physics of color centers provides a valuable probe into the nature and dynamics of the alkali halides and alkaline earth oxides and alkaline earth fluorides, all these related. F prime center. So, this is an anion I can see with 2 electrons. So, the F dash center is one possibility. Then you have the R center, R1 center, the M center. The M center is F center with a pair of vacancies. Of opposite sign. Then you have also an R2 center here. These are involving 3. R1 center is an F center combined with anion vacancy. R2 center is 2 F centers. Then you have a V center. These are holes trapped in cations vacancies. The most well known type of center of this kind is the VK center. So, this can be generated just by heating alkali halide crystals in halogen vapor. So, the absorption spectra of the different types of centers in KCl are shown in the next figure, and the composition of the different types of centers. the M center, the VK center, the H center. H center is similar to the VK center, but it is in an interstitial state. And the FA center in which one of these 6 nearest neighbor positive ions surrounding a negative ion vacancy is replaced by an impurity ion. One of the 6 nearest neighbors replaced with an impurity ion, which we call A. So, these are the different types of color centers which produce a rich variety of optical absorption, bands and spectra, which can be used to probe the solid as well as to produce devices of different kinds. For example, photochromic glasses which are used in spectacles, they are made using F centers. We now come to the third type known as the interstitial atom or Frenkel defects. This is shown in the next figure 38(5), and here an atom or an ion in the lattice is displaced from the normal position to a position which is inside the interstices. So, these are known as Frenkel defects. Again we can find by similar argument that the concentration, equilibrium concentration of Frenkel defects is given by n prime exponential minus E by kBt. Now, n prime is the number of interstitial sites. This is because the pushing of this restores charge balance, and that is a constraint which has to be used in conjunction with the minimization process of the free energy. So, usually in ionic crystals cations are usually much smaller. So, usually it is the cations are transferred into interstitial sites. For example, silver chloride. Silver is a very small ion, Ag plus. Then calcium fluoride, zinc oxide. These are examples of solids which have Frenkel defects. These are created while growing the crystal when the molecular formula does not conform to the stoichiometric ratio. So, for example, in zinc oxide there is one zinc ion for every oxygen ion, that is stoichiometric ratio. During the growth of the crystal, suppose the molecular formula becomes ZnYO, where Y is greater than 1, then it is non-stoichiometric. This non-stoichiometry means that there is an excess of zinc ions in the crystal, and these occupy the interstitial. Excess zinc occupy interstitial sites. Frenkel defects of this kind can also be created by bombarding with high energy radiation. In a monatomic metal lattice, an interstitial defect may occur when the atom in a lattice site migrates from the normal position into a small void position. So, they are self interstitials, producing large distortions around the interstitial site because of the size of the atom. So, this is not highly probable. So, usually their concentration of such defects is very small. We then come to the fourth category of point defects, namely impurity atoms. We have already discussed them in connection with semiconductors. So, for example, phosphorus doped silicon. So, the phosphorus is a pentavalent impurity. So, doped into silicon which has 4 tetrahedral orbitals. So, you can have a substitutional impurity which means that the impurity atom simply goes into the position of the host atoms. In order to do this, the atomic radii should be comparable of the impurity atom and the host atom, and the crystal structures of the both should be the same. For example, copper nickel, the copper nickel alloy, and then of course the n type and p type semiconductors. So, these are standard examples of such impurities. You can also have a situation like carbon added to iron. That gives you about 2%, say. These are parts per million level. So, when this is done, you have interstitial sites for the impurity. For this reason, the composition cannot exceed, concentration cannot exceed, say, 2%. So, optical absorption, birefringence, electro-optic coefficients, all these can be modified. So, the presence of effect of point defects on the properties of crystals are, for example, if we have vacancies present in a solid, that means that the density will automatically get reduced, and therefore, the bulk coefficient of thermal expansion will increase due to the presence of the vacancies. The heat capacity of the crystal also increases due to vacancies. If you have a pair of vacancy like a Schottky pair consisting of charges of opposite signs, then it acts as an electric dipole. So, this dielectric dipole moment causes a change in the dielectric constant, and as we have already seen, the presence of color centers such as F center and other such centers affects the optical absorption properties of crystals, and crystals that are normally transparent appear colored when color centers are present. The presence of impurities, for impurity atoms, also modifies the behavior. For example, carbon added to iron improves the mechanical properties. In semiconductors, we have already seen that doping N or P type doping changes their conduction property substantially. So, these are the various effects of point defects on crystal lattices. In the next lecture, we will consider line and planar defects.